Hi, good morning and happy festivities. Welcome back to GD's Science Bites. I thank all the viewers and those who have liked and subscribed for this channel. Today I'm going to walk you through another very interesting video on the culinary, gastronomy and chemistry of carbs or carbohydrates. Now before we go into the chemistry, let's look into what are the general carbohydrates that one consumes during a typical day of breakfast, lunch, dinner and maybe the evening snacks. Now carbohydrates along with protein and fats and lipids, they form a very important part of the macronutrients as we know. And carbohydrates are really hip and happening macronutrients because as far as their structure is concerned, they have a wide range of structures and hence the chemistry, the properties are all quite interesting, quite diverse, quite varied. Now when we start with carbohydrates, the simplest of the carbohydrates is of course the glucose that all of you are aware of. And along with the glucose, you have other monomers. By the way, glucose is called as a monosaccharide because it is a single structured or a single molecule there. Now, along with glucose, you have some others like, for example, the fruit sugar fructose, which is also a monomer. You have galactose, which you may or may not have heard of, but I'm sure you've heard of milk sugar lactose. Now, lactose is a disaccharide. It's made up of one molecule of glucose and galactose. Similarly, maltose is made up of two glucose units. Sucrose is made up of one fructose and one glucose unit. Along with this, let's say, imagine there's a ladder. So you have the monosaccharides, you have the disaccharides, and then let's move on to the trisaccharides. Where do you get the trisaccharides from? So imagine you're having beans, you're having sprouts, right? So beans, sprouts, different types of beans. You have kidney beans, lima beans, so on and so forth. So all these beans family, they give you raffinose and stachys. They are typically what we used to call as roughage, we used to call as also sometimes dietary fibers, right? So these are smaller dietary fibers which are trisaccharides in nature, meaning they have three units, three typical monosaccharide units in them. And then we have something which is, I think probably many of us are aware of it, which are called as prebiotics. Right? You have probiotics and then you have prebiotics. We're going to discuss probiotics later in my other videos. But today let's stick to prebiotics and the dietary fibers. So typically the dietary fibers, also carbohydrates, they are longer carbohydrates, meaning slightly higher up from stachys and raffinose. So now we have what is called as prebiotics. We have galactose oligosaccharides, we have xylose oligosaccharides, we have fructose oligosaccharides, so ZOS, GOS, FOS, etc. These oligosaccharides, meaning that the monomer numbers now increase from 2 to 8 or 10. Right? So you have glucose, galactose, then you have lactose, maltose, then you have stachys and raffinose, and then you have oligosaccharides. And then is there anything else? Oh yes. The topmost rung of the ladder is occupied by what we sometimes call as polysaccharides, and sometimes we also call them as complex carbohydrates, which are basically starch. Starch is very important dietary source of carbohydrates, and along with starch, when we consume plant-based food, we also consume not metabolize, but we consume cellulose. It is digested and metabolized by the gut microorganisms. We also consume pectin. And from animal source, do we have any carbohydrates? We usually think that animal source food is usually protein based. No. We also have a carbohydrate which is glycogen. Right? So these are typically the carbohydrates, and as you will be able to appreciate that the type of carbohydrates are different and hence the structure is different, and obviously you expect that the chemistry is different, the chemical properties are different, and that's exactly why you see so many different culinary creativities that can come out of these carbohydrates, and hence the gastronomic delight. Right? Okay. Now, before we have to discuss all the carbohydrates, yes, I agree, but since carbohydrate is such a huge family, let's take up one step at a time. Let's walk from right on the top of the ladder. We have the starch. So I'm going to take up starch in this video a little more in detail. Now, before I go into the details of the chemistry of starch, I would like to know how many of you are aware that the structure of starch granules which come from potato source is very different from the structure of starch granules which you get from rice or wheat. Did you know that? I'm sure you didn't. So yes, that's true. The starch powder looks the same, white powder, but have you noticed that a sago starch differs or behaves differently when you cook it? A potato starch behaves differently. The rice or the wheat, the oat, etc., they behave quite differently. Now, and very interestingly, when you put it under the microscope, the starch granules, when you isolate and put it under the microscope, yes, we can put starch granules also under the microscope. It's not only the bacteria or the fungus, we can put others also under the microscope. We food scientists put a lot of things under the microscope for our evaluation and analysis. Now, when you put that, you find that the rice starch is very, very small granules, whereas you have corn starch which are quite different and they have a polygonal shape. Similarly, I'm not sure how many of you are aware of sago starch. They are large elliptical. Some of them have disc-shaped structures. Some of them have smaller polygonal structures, right? So you can see that on the slides. On my slide, you are able to watch, I'm sure, that these structures, they vary depending on the plant source or depending on the origin of the starch. Interesting, isn't it? Now let's come to the chemical structure. That was the microscopic structure. Let's come to the chemical structure. Do they vary there? Well, yes and no. Now, all starches are made up of broadly two things, which is called as amylose and amylopectin. The amylose and the amylopectin, all of them are made up of glucose subunits. That's why starch is called as a homopolymer, meaning that the starch has single type of glucose or single type of monosaccharide, which is in this case glucose. Now, the difference between amylose and amylopectin is very simple. So imagine that you have a string of pearl. So the string of pearl, so the pearls are glucose and the string is the alpha-1,4 glucosidic bond. I hope I'm making myself clear to you. So imagine in that string of pearl, you are stringing in the glucose units. All of them are glucose. You have the string, which is the bond, the chemical bond, which is an alpha-1,4 chemical bond. Right? Now, that is what makes the amylose a straight chain structure. What is the difference between amylose and amylopectin? The amylopectin is somewhat similar to amylose, meaning that it does have the string of pearl, that is your alpha-1,4, but to that string of pearl, imagine that you have a second or a third or a fourth string of pearl. How are you going to attach that? That is attached through an alpha-1,6 branches. So, effectively, while amylose is a straight chain polysaccharide, and amylopectin has straight chain, along with that it has branches, and the branch points are usually the alpha-1,6 bonds, right? And the sago starch, the potato starch, the rice starch, the wheat starch, even in the rice itself, there is glutinous rice, there's sticky rice, then you have basmati, which is very discrete. They stand on their own alone, right? So you have very well separated rice. So why do you think this happens? After all, rice starch is same, right? So this happens because rice, sago, wheat, tapioca, cornstarch, all these have a different composition of amylose and amylopectin. No two starches will have the same type of composition or ratio of amylose and amylopectin, and because of this difference, it adds to their chemistry, it adds to their differentiation in chemistry, it adds to the culinary as well as the gastronomic differences which you find among the starch. I hope that's clear to you. Now let's move on from the structure to the chemistry of the starch. Now, whether you have taken a rice starch, a wheat starch, a sago, or a tapioca starch or a corn starch, three major reactions of starch are common to all these. These three major reactions are gelatinization, retrogradation, and the dextrinization. We are going to discuss these three a little more in detail. Right, so let's start with the first chemical reaction of starch, which is the gelatinization. In order to understand the gelatinization of starch, you have to imagine that you're putting the, let's say, potatoes, right? And let's say you put this in a saucer and you start the stove. So the reaction that you have initiated is starch along with water at an increased temperature. So starch is starting to react with water at a heightened temperature. Now remember what I told you, that starch granules are very, very tightly coiled and very, very compact structured. So in such a compact structure, you expect that the amylose and the amylopectin, remember the complex polysaccharides which we divided the starch into, so those chains are going to be very, very compactly arranged. They're not going to be loose and they're not going to be dainty like the string of pearls. They're going to be very, very condensed structures. The minute you start the temperature and the water addition, what happens is the water starts to get into the granules of starch, and slowly the amylose starts to take up the water molecule. So the water gets into the starch granules and then there is a swelling of the starch granule. Now this swelling of the starch granule, of course, is also facilitated with some of the bond breaking. Slowly you have more and more water getting inside, and that's why you have a swelling. So that's exactly why you find that the hard texture of the potato has now started to slowly soften. A boiled potato is soft, and that's exactly why you are able to mash it up and you create your own gourmet meal. Similarly, you have rice. When you boil the rice is brittle. Raw rice is brittle. It's not something that you want to consume, right? So what do? You boil, and that's exactly what you do when you are boiling and cooking the rice. You are gelatinizing the starch. Fine. If you do not want to take these example of potatoes and rice, take the starch powder. The same thing happens. Remember when you want to add it as a thickening agent, etc. So what do? You take the starch powder and you start to mix it in water. The minute you increase the temperature, mind you, this doesn't happen without a temperature addition. You have to increase the temperature, right? If you watched my earlier video, we've discussed this, that starch on its own is going to act as a suspension, and slowly when you add water, the starch is all going to settle down. Nothing much happens without the addition of temperature. So this gelatinization reaction is facilitated, or has to be facilitated, has to be catalyzed with the addition of temperature or with an increase in the temperature, right? So now when you have starch powders and you have put into the water and then you are starting to heat, the paste, the starch paste, starts to increase in its viscosity. That basically means that the starch granules or the amylose is now starting to accept water, is now starting to get into the, water is going to get into the amylose. As you continue to heat, what will happen as you continue to heat this starch powder? As you continue to heat, you will see that though there was an increase in the viscosity earlier on, with prolonged heating, however, you find that the viscosity of the starch base starts to decrease. Why? What happened to the water? Now, nothing happened to the water per se. Water is there, but what is happening is the temperature is now raising. Remember, the temperature has gone beyond a certain range, and interestingly, you are initiating another chemical reaction, which is bond breaking. What kind of bond break? We have the amylose, which has an alpha 1,4 linkage. Remember, amylose and amylopectin all have alpha 1,4 linkage. So the minute you go on increasing the temperature, the alpha 1,4 bonds start to break, right? So that's exactly why the connection or the network which had formed earlier, a very strong, very tight network which had formed earlier, started to loosen up a little bit with the addition of water. So you found that the viscosity increased, but finally it started to dissociate because the bonds started breaking, and that's why there is a reducing of viscosity, there is a reduction in the viscosity as you go on heating the starch powder. Correct? Alright, I have added temperature. What happens when I reduce the temperature? Or in other words, what happens when I cool the whole thing down? Do you expect any change? Do you expect any chemical reaction? Yes. What is going to happen is the starch molecules come together, or the amylose come together, and you have a re-thickening of the paste. Now, the gelatinization of starch is a property which is used to characterize the starch, because different starches have different amylose and amylopectin ratio, and hence the gelatinization temperature also varies. In general, it's between 52 to 60 degrees centigrade. That is the general temperature range. But depending on what is the starch, depending on what kind of starch, what is the amylose and the amylopectin ratio, each different type of starches will have one particular gelatinization temperature. And mind you, the gelatinization temperature of starch can also be influenced, can also be affected with the kind of environment that the starch is in. Means what? Means here is where your culinary compounds or the culinary activities will come into picture. Let's say you are adding starch as a thickener for a custard or for a soup. So in these cases, usually the starch powder is added along with, let's say you are making a custard, so you have the starch powder is now going to be added along with milk protein. What do you think milk protein will do with its gelatinization temperature? Usually the milk protein tends to lower the gelatinization temperature of starch. Similarly, let's say you are adding tartar, or let's say you are adding citric acid, the lime juice or other acidic juice in your soup. In such cases, then because of another reaction which sets in, the starch paste is going to have a thinner consistency, or in other words, the viscosity will decrease. Now, what is that? So you have starch, you have water, you have temperature, and along with that you are also adding acid. Now acid, just like temperature, acid also tends to break down some of the bonds, and that's exactly what is going to happen when you start adding acid onto your starch paste. So it's going to break down the alpha 1,4 bond or the hydrogen bond which the starch may have made with water, and that's exactly why you see a thinning of the paste. Starch paste is thinning because of the addition of the acid that you have, right? So do we have a solution for this problem? Yes, you make the starch paste, you gelatinize it, you finish the gelatinization process, and then you add the acid to it. Then your starch paste does not go into the thinning. Now, gelatinization of starch can also be influenced by sugar, right? So when you're adding sugar, remember sugar, salt, these are all small molecular weight compounds which have higher affinity towards water. And since gelatinization of starch is dependent on the amount of water that can go in, that can bind, obviously if you create a competition with an ingredient like salt or sugar, obviously you expect that the temperature at which the gelatinization will happen is going to increase. So the gelatinization temperature goes up because the compounds that you've added, or in your case let's say the ingredients that you're adding, is also competing along with starch for water. Now let's look at lipid. Lipid has a completely opposite effect as far as gelatinization is concerned. They tend to lower the gelatinization temperature, and they tend to make the paste a far more thicker paste when you have added a lipid. So far, therefore, we have discussed at length about the gelatinization of starch. Let's go to the next very common, very annoying reaction that we see, which we call as, in food technology term, we call it as retrogradation of starch. Now, retrogradation of starch begins when we have the starchy molecules, or when we have the starchy food, a fresh made starch food. The starch is in its amorphous form. Please understand that amylose, amylopectin, they are coiled, they are highly condensed, they are compact, and they are in their amorphous forms. The minute you leave the starch a little bit, maybe in the ambient temperature, or even worse if you are leaving it in a refrigerated condition, then the amylose and amylopectin, they tend to, especially the amylopectin, they tend to go into a crystalline form. So this alteration from an amorphous to a crystalline form is called as a retrogradation of starch. Now, I said that it is an annoying reaction. Why do you think it's an annoying reaction? Because retrograded starch, the importance is that you will find that the bread, when you have kept it maybe for a longer than what you should have kept, the bread starts to crumble in your hand. I'm sure you've had that annoying experience. So that's the reason, or that's the point where the starch has gone retrograded. Retrogradation of starch is also in layman language called staling of bread. So there's a huge science behind anti-staling agents, the use of enzymes for delaying retrogradation. So I'm going to have a dedicated video for that. Let's move on to the third important reaction of starch, which is dextrinization. Now, dextrinization of starch is to do with heating the starch in absence of water, just the opposite of gelatinization, which has water in it. But here in dextrinization, you observe the changes, you observe the chemical reactions and the changes attributed to that because of the absence of water, however, because of the heat that you provide. Now, a very interesting feature of baking is the browning of bread. I'm sure all of you have eaten different types of breads, and have, at least some of you have noticed the different varieties of browning. Not everything is white, not everything is brown. There are gradations of browning. So this browning of bread, or the browning of baked compounds, are usually because of the dextrinization of starch. So basically, dextrinization means that when you are heating the starch, remember, in absence of water, there is no water molecule being added, there is no swelling. What is happening is that the starch, or the amylose and the amylopectin, especially the amylose, they start to, the alpha 1,4 bonds start to break down because of the heightened increase in the temperature. Imagine you are doing a baking, so baking temperatures are very high. So because of this, the starch starts to break down, especially the amylose starts to break down into smaller chains, which we now call as dextrins. So the formation of dextrin, and hence the name dextrinization. And formation of dextrin is also very important in beer making. So in case of beer making, when you have the malt being made from barley, so there is a process where you have kilning, the oven treatment. So in the oven treatment, what we basically do is we try to break down the starch into dextrin. That adds to the full-bodiedness of a beer, remember? So dextrinization is a process which is important both with respect to baked goods as well as in the brewing industries. I hope these three reactions are now clear. The importance of these three reactions are clear. If you have any more clarifications required, if you need to know anything more, please put down those on the comment box. I will be very happy to field your questions and to give you the answers, because as I answer your questions, I also learn a lot. So I come now to the end of this video, which has gone on already pretty long. Please PLSSC, please like, share, subscribe and comment. I look forward to all your comments, and I hope to meet you again very soon, probably next week, with the part 2 of this video, where we are going to continue discussing the carbohydrates.